Okay, so today we continue to give you the introduction for the transformer. So I want to ask before listen to my course about the transformers. Do you all of you know the transformers, how it works? So 你们都知道 transformer 大概运作的机制吗？大概好吧。Okay. So I hope if you don't understand my English when I give the lecture about the details about the transformers, now I will make a recording. Okay, for it. Last week I also made a recording, but the quality is not very good. So sorry. So this time I try to make a recording again. Okay, so I will put it on YouTube and notify you. Okay, so that you can take it as for your reference. Okay, so let's start. So last week I introduced the transformer using the original paper's framework like this. And okay, so in fact, what is the attention mechanism in transformer? Okay, so basically is attention. The idea of attention is try to match a query and a set of key value pairs to an output. So it means you can think that each query, key, and the values actually they are the vectors, a set of vectors. Okay, so these vectors I want to give you a query, and the query will compute the similarity between the key, and according to their score, the similarity score, to do the linear combination with the value vector. So the basic idea is like this. Here is the formal method exploration how to compute the attention. You can see the attention mechanism. Here we have Q, K, B. You can think each is a vector. But if you want to make it more efficient, actually Q can be a set of vectors. K and B are also a set of vectors. So they actually can become a matrix. You can perform a matrix multiplication. It make it very efficient to be computed in GPU. Okay, so but when you try to understand the general idea, you can think it's just a vector. Q, K, B, they are three vectors. Okay, how to compute them? Their attention value. Okay, so here is the equations. The equation like this: Q times with K is actually the inner product between them, and because the scale is usually very large. Okay, so we will divide it. We like to do a normalization to scale it down, and the normalization is divided by the square root of the dk. Dk is the dimension of the vector, of the case vectors. Okay, and then after the normalization, then you can actually represent the similarity score between Q and K, and so we can use their similarity score to time with the B. B is here. You see B is here. Okay, so B is also a vector. So you now, after the transformation, the attention transformation, you can get a new vector. The new vector is computed like this. Okay, so here is a figure to illustrate the idea. Okay, Q and K, they perform the multiplication and the scale is down. Okay, by this. And then if we are doing some masking attention, so you can perform the masking here. It's optional. And then perform the somax. Okay, you see here is somax. The somax is turned into a probability distribution. and then finally it's time with the matrix V together. So finally we output the new attention values. Okay, so it's the general idea of attention mechanism. Okay, so but they propose you can see in their figure here they say it's a multi-head attention. Multi-head. Okay, multi-head means I can have multiple heads. Each head they can perform their random weights to do the attention calculation. Okay, so in this case, multi-head means I will perform the attention mechanism several times. So you see, so each time, suppose in this case, the QKB, okay, I will throw a linear projection to project to a smaller space, a smaller vector space, and then in each space I perform the attention again, the similar, the same mechanism here. Okay, I will do it on different heads each times. So in this case, in the papers they use H is 8 heads. Okay, I use 8 heads so that I will compute using the same QKB but with different linear projections. Do it 8 times. Okay, then when I finish, each time I will calculate a new vector, right? So after it, I will concat all the 8 attention vectors together, and do the linear to output my final attention. Okay, so the expression is written here. You can see the multi-head attention QKB. Okay, actually it's a concatenate for head 1 until head H, and the time is WO. WO here means linear. It's a linear projection. Okay, so what is the H1, H2 until H head 1, head 2, and head H. Okay, each one head, for example, head I means the I's attention process. It's ties, you see the Q ties with W. WIQ is actually it means the WI is the I heads weight. You can think it's actually like a linear. It's like a linear model. It's a linear layer. Okay, so we use the WI to project Q to the I's head. Okay, and the K, it has its own WI of K to project the original K to I's space. And also V, time with the WBI to project it to the I's space of V. So each one, I perform in the individual attention mechanism. I will repeat it H times. Okay, so after I get the head, after I perform the attention for each head here, and then I will just concat them together. Okay, so do you understand the idea?
For the case of self-attention, QKB are actually the same matrix usually for self-attention.
QKB, they are from the same source, but they will be projected to different space. Yes, by using the W for QKB, before they are the same, they are derived from the same, but they will time with different matches. Okay, Q will be timed with the WQ, and the K will time with WK, and the B time with the WB. So they will become different matches, then perform the calculation. Okay, so So here you see the original QKV. Actually, they are the Q. Q is 512 dimensions, and the K. Okay, they are all the same dimensions. Okay, but before they are divided. They are derived from the same data. Like I can call it I should call it it's a vector called a token. Okay, any token is vector. But the token will time with the WQ to becomes Q, and the token will time with the WK to becomes K vector, and the token will time with the WV to becomes the V vector. Okay, it's the self-attention. Yeah, because I use the same token to generate different W, Q, K, V by using the correspondent WQ, WK, and WV matches.
But usually it will be a sequence of tokens.
Yes, but here I just only use one as an example. Okay. But you can expand it to be you can become matches. Okay, each token is a vector. You see, so if you have many tokens, actually you can just arrange them as a matches. Okay. Yeah.
One more question. Query and key, they look symmetric. How do the model know that I'm query or I'm key? Because they come from the same source.
They will from different pathways.
Oh.
Yeah, the Q is from this, K from this, they from different pathways. Okay, you can see that in this, here's the Q, K. Okay, so they have a different pathway. Q and K will time together, and finally use their similarity score to time the speed.
So I mean, this matrix multiplication is not product. So
yes, actually,
K or KQ, they are kind of the same. So how do they know that I'm query and I'm key? So,
but
why separate?
Okay, I think in self-attention, it's okay if you change the order, the results the same. But in later, okay.
Or general.
Okay, in these videos, if for self-attention, Q and K are the same, and then they can switch their orders, no problem. You will not get wrong result. It's okay. But if in here, in this attention, you can see here is also a multi-head attention here. Multi-head attention is all here. But this multi-head attention, it accepts the input. The K is from the decoder, but the QV is from the encoder. They're from different way. Okay, so at this stage you cannot change
different things.
They are different. Okay. So later I will go back to show you again.
Thank you.
Okay, so let's see go back to see the multi-head attention. Okay, so alright, so you give you a token. I will transform it into Q, K, and V. Okay, then the Q, each one, Q I will throw a linear. Here is a linear. It's a linear. You can think it's just actually it's like a projection. Okay, so I throw the linear. I will project the Q to be here. The Q becomes because in their papers they only 8 hits. So actually they will divide you can think the new dimension will be 64 dimensions. In the small q, I call it the q1. Okay, for k, okay, it's a small, let's call it a k1. It's also 64. It's a v1. Like this. Okay, the dimension is reduced. Okay, so the linear. Okay, the linear is, you can think it's just a linear layer. Okay, the linear layer you can change the dimension, right? So the multiplication can change the dimension. So it's from 512 dimension and reduced to 64 dimensions. And you repeat to do it. Actually it's a random projection. So for Q1, for Q, you just project to Q1, and you can do it for Q2, for Q3 until Q8. Okay, you can do it 8 times. Okay, so then after for each Q1, K1, B1, we do the same. Attention here you see the attention. It's attention for, you can think it's attention for Q1, K1, and V1. Okay, and I repeat it 8 times. Okay, so the output will be as a new vector. I call it a new vector, attention vector. Q hat 1 is also 64 dimensions. But I just repeat 8 times, so you will have also have a Q1 for Q2. Sorry. For Q2 is also 64, and Q3. You have so many, in total 8, the new attention Q vectors, and you just concatenate. You see the final is a concat. Concat them together, they will turn into a 512 dimension again. Okay. So it's possible to call the multi-head attention. The idea is if we only do one attention here, so it's they think maybe because of the attention, the initialization of the attention matrix is actually random. You use a random matrix to start your attention, and after some training, you will fine tune your weights. Okay, but they think if I can add some variation, make it more diverse. Okay, so this is why we repeat it 8 times. Each time I use a different random matrix to produce the QKB. Okay, so the main idea is try to increase the variation, so that maybe I can find some variations can perform better in the attention in this attention mechanism. Okay, the main idea is like this. 它主要就是要增加它的多样性因为如果说你只用一个 attention 的话，它就只是用一次的那种乱数去产生出来的 QKB， 那它就这样子做8次，所以8次里面总会有几个是比较好的，那这个效果比较好，就可以提升它的那个准确度。那主要意思是这样。To aid is variations so that maybe some attention heads can perform better, then it can improve the overall accuracy. Okay. Okay, any problems? Okay, so this is what we call multi-head attention. in their paper, in Google's paper, their attention model actually they have 3 different attention mechanisms. Okay, the first is the encoder. Okay, in the encoder it performs the self-attention. So in self-attention is each token will attend other positions tokens. So I can attend all the others for you. So that I know what's the relation between me and the other tokens. Okay, and I can get the other tokens' weights and the similarity scores to generate a new attentive vector. Okay, so it's encoded. The first, the self-attention, and the second is the decoder. The decoder performs the masking self-attention because it will have to follow the autoregressive way to generate your next token. Okay, so I think we already explained in last week. Okay, so you try to attend all position of tokens in a token, but you have to only attend on your current token and the previous token, but you cannot attend to the next token. And the third attention mechanism is called encoder-decoder attention. Sometimes we call it close attention. Close because it close from encoder and the decoder. Okay, it allows the position in decoder to attend all the position in your input sequence. And then it tries to mimic the sequence-to-sequence model. Okay, so let's go back to these figures. I can show you, give you a general overflow, again to illustrate the 3 different attention mechanisms. I will use the same examples. Use "I love you" and translate it into Chinese. 我爱你. Okay, I use it again. When you read the original transformer papers, they use, actually the paper is very, very concise. They write it, but they miss many details in their papers. So you have to check their code to see what's actually they are implementing in this idea. Okay, so just read their papers is not enough. You have to refer to other information or to look into their code to see what's the actual implementation, how to make it workable. Okay, so we say we have 3 different attention mechanisms. So the first one here. First one is here. It's the encoder. Encoder's attention. Multi-head attention here. It's the first one. Okay, so the first one, suppose our input data is I love you. Okay, I take this example for training. In your training phase, your input is I love you, and your output, output will be is our label for the English sentence. Okay, so in training phase, I know the correct answer, right? So it's my input, it's my output. Okay, here, so I love you. So in the encoders, so actually you will have I have a Q. You see, here you see we have 3 arrows represents Q, K, and V. Okay, so you know QKV is project the original token. I love you. These 3 tokens, they are project to generate the Q, K, and V here. QI, Q love, QU, and also key. I, K love, KU, and also I generate it's called B, I, love, Okay, each the Q, K, and the V, they are vectors. Okay, I arrange them in a matrix form. Okay, so Q in time is K. You can compute you can get their inner product as their similarity score. Okay, so let's suppose the similarity I give here. Suppose it's here is the 6. This and this is. I use it as an example. Okay, so it means after the normalization, you see attention will finally do the softmax. Okay, so it's like normalization, your probabilities. Okay, so finally you can see the similarity score between for token I, the similarity score between Ki, K love, Ku is 0.6, 0.1, and 0.2. Okay, so suppose the probability distribution is like this, and I will time with our value vectors. Okay, so you can obtain your final score. I traced. After I use this similarity score time with your value vectors, you can get Q. Actually, is okay, the new attended vector Qi is actually the 0.6 times Vi. You see, 0.6 times Vi and plus 0.1 times V love. You see, and plus 0.3 times Vu here. Okay, just simply multiplication. Just multiply this vector with the 3 value vectors. And then you can write the same equations for Q love and QU. Okay, so I will skip it. Okay, but I think you already know how to express it. Okay, just express it in a similar way. Okay, so it's called the attention mechanism in encoder. Okay. And how about decoder? It's another decoder. Sorry, in decoder's attention, here is our decoder. Here is also again is a multi-K attention, but it's a masking. So it's slightly different from the encoder's multi-K attention. Okay, so next week we talk about how to do the the mask key, right? Because I cannot attend your next tokens. I cannot attend because I have to follow the auto-regressive way to generate the token one by one. So I can only attend my previous token, but I cannot attend to your your next token. So I have to just a slightly modification here. So we just mask your future tokens. So it means I can only attend I, but it cannot attend love and you, because love and you are future tokens. So you cannot attend them. Okay, so with this method, you can then when you do the normalization, okay, so the probability will be changed. Because you have to skip the probability between the other tokens. Okay, so we change it. Okay, so here the probability becomes like this, and for the Q love, the probability becomes like this, and this maybe okay, the same. Okay, so based on the new matrix, then time is your value vectors. You can change. So in your decoder, how to calculate your Qi, your new attended vectors. Please follow the new probability here. So here you go. Time with your I. We erase love and you. And how about Q love? Okay, it becomes like this. Got it? Okay, Q love. We only attend Ki and K love. Okay, so I can generate the new attended vectors for Q love like this. It's for decoders. And how about for the third attention mechanism here? Here you see. It's also a multi-A attention here, but we call it a close attention. It's not self-attention. It's called close because you see, is Q is from your decoder. This is Q here. In the original figure, the paper's figure, they don't say who is QKB, but you have to check their code and what's the for K and the B are from here. You see, here. So this is a K, it's a B from the encoder. So what we call is a closed attention. Okay, so if you want to perform this matrix will look like this. Your Q is now your Q is from your output decoder, right? And this is a decoder. Here your decoder's output is 我爱你. Okay, so it's different. Sorry. When I illustrate the decoder, it should be changed. Not I love you. For decoder, here your decoder is 我爱你. So I forget to change it. Okay. So your Q is 我爱你, but it's sort the first masked multi-head attention method. So it's already I add a head. I add a head here to represent that already passed the first attention block. Okay, so now becomes a head Q like this. And for the I love you, K is from here, from your encoder here. So I love you. So they also Okay, so this is K from the encoder. They also pass from the first self-attention here, and it becomes head K, I, head K, love, head K, U. And what's the V? V is also from encoder. Right? So, okay, so here, K, so head K here. Okay. And then we perform the same calculation. But here we don't perform the masking. No, we don't use masking here, so you can just check all of them together. Okay, because they want to simulate a sequence for I and I love you. Okay, they want to just attend all the decoders output want to attend all the information from the encoder. Okay, and the masking is already performed in the first attention of the decoder. So in the close attention, they just remove the masking, the comparator here. Okay, it's their design. Okay, so here I can simulate. Oh, it's very dangerous. Okay, so suppose my calculation for the close attention between from the decoder to attend the I love you from decoder. Okay, and then I perform it. Then I calculate. Okay. It's a new calculation here. I perform like this. It's a double hit. It's because they attend twice. Okay, several times. War. Okay, Q of war. And the new calculation would be like this. Okay, so the same as we have shown for the encoder's self-attention. Okay, just take the probability. Okay, time with the value vectors. Okay, you can generate a new vector, attended vector representation. Yeah. Okay, to just repeat for x is I. And then, okay, we can do it for the other two tokens here. Okay, so after you obtain, you will repeat this process 6 times in the table. They have 6 blocks, attention blocks. So you will repeat 6 times, and after that, finally you will throw a linear. You see, there's the next layer is the second to the next layer. We call it the penultimate. The penultimate layers is called it's a linear. So each one you throw I use this one. Okay, so I use this token. Use these vectors. Okay, so from here, so linear, and finally I do a softmax. The softmax is you can think it's I want to do a classification. So suppose I have a dictionary. Dictionaries. A dictionary contains several words. I have to do the classification to to predict the probability to each word. Okay, so here. Okay, so the word throw a linear layer, and then I will do the softmax here, and I will generate. Suppose I have 5 words in my dictionary. Okay, so the first one is walk. Okay, suppose I have 5 different words in my dictionaries. Okay, so then I will use this to do the prediction. What is the next word after I see this token and this attending matrix? Or suppose my prediction is like this. Okay, suppose my prediction like this. The probability prediction like, and which one is the highest? Make someone is highest here. Okay, this token has the highest. Okay, but because it's training. Okay, so in training actually we have the ground truth. So actually you know the ground truth label is okay, suppose it's like this. Suppose like this. Okay, I know the correct answer is this. And my prediction probability is like this. So I can calculate the close entropy between them to modify, to fine tune our model weights. Okay, this is for training. Any problems? Okay, so how about for inference? If we only do a test on inference. Okay, just follow the similar way. Okay, you have input, I love you. I use the same example again, but this time we are doing test. It's an inference. So just follow the same way, we will get through the encoders, multi-head attention, and here you encode. But remember, in your decoder, you don't know the answer right now. Okay, so because it's now you are going to do inference. Okay, you don't know the correct answer. Okay, so you have to predict. Okay, so now you have to only you have to in your decoder you have to. If currently I use this token, I generate the first token war, and I want to predict the next token. Okay, so in this time here I only know in my decoder I only know like this. Okay, because currently I get that my current token is war, and in decoder here, in the first attention, the masking, and you actually don't perform the masking because you only know the current, you just output the war, so you own the only tokens is war like this. Okay, so then I can calculate the probability here. And then time with your vector. Okay, so then it's for the decoder's masking because you only attend my current tokens, and the time with the back value vector of wall, and then pass it as your queue. And in your queue, you will attend. Please just match, just ignore the second row and the third row, because you currently don't know your prediction for next token. Okay, so you just calculate. Use your calculate. Attend the vector here, and to compute the close attention with the formula encoder here, and then you can generate your new vector here, and then to predict again. But I want to put you a wrong prediction here. Suppose I make a wrong prediction. My prediction like this. Here it is. Okay, here. Now the highest probability is another word. It's wrong. Okay, because the I love you should choose I. Oh, but he predict a wrong word here. Okay, he predict a hate. I hate you. It's wrong prediction. So hate. So hate. Okay, so your prediction will be wrong, but because it's in inference stage, so the system, the generative AI, it doesn't know it's correct or not. It just generates one by one tokens. Okay, although it generate a wrong answer, but you just continue with the wrong token to do the next prediction. Okay, so your next prediction will be, because you generate the next word is, okay, I have to say it's wrong. It should be this word, but it's wrong during your inference stage. Okay, but the system doesn't know. Okay, just follow. Okay, so here you will use this token. Okay, to compute the similarities. We just repeat the same process to do it. But in training, you can correct it because you use supervised learning. You can correct it, but in your inference, you cannot correct it. You just use the wrong information to predict your the next token. Maybe it becomes a disaster. It's totally wrong. You can see if the next token is wrong, and the next two token, next three token are totally wrong. Like this. Okay? Because when you generate a wrong token here, you will use the wrong token to generate this next attending vectors. Got it? Okay, so this is the whole process for the attention for the transformer, including the training phase and the test phase. Okay, any problems? So I think because the most important part and you should take away when you read the transformer paper. Okay, so it's an attention mechanism. So you should know how to use this attention mechanism. You can when you design your own system, you can combine all the three different ways to design your attention system. Okay, there are many transformer families. I just list some famous transformers here. First one is BERT. It's also from Google. It's a bidirectional encoder representation. So it means it's an encoder. It's only used encoder part. Actually, you can use the BERT to do the transformer to generate any embeddings you want. Okay, so suppose you have English or Chinese or Indian language or any language, you just input to a BERT. Okay, the BERT will transform each token into a representation. Okay, so the representation you can use it because it's encoded, so you can use this representation to do the next what you want. Okay, so they published it in 2019, and it's based. Its base model contains 110 million parameters, and the large model contains 340 million parameters. And the next, because the transformer just inspired many related systems. Okay, the GPT. GPT is it's published by OpenAI, so it's called a generalized pre-trained transformers. But it only uses decoder part because they think the decoder part is already strong enough, so they just skip the encoder part. Okay, so in their versions, the GPT-1 contains 117 million, but GPT-2 becomes 1.5 billion parameters, and the GPT-3 is 175 million parameters. You cannot drop in your personal computers. It actually, all this model is too huge. You cannot train it. You just use the pre-trained model and connect to your application, to your task. You cannot train again because the training is take a lot of computation resource, take a lot of time, a lot of money. And okay, so for GPT, after GPT-3, it's not open source, so you cannot use their model. Okay, but Llama is provided by Meta. Okay, it's called a large language model Meta AI. It's open source, so all the versions are open source. You can use it. It's also a decoder-based framework. Okay, so Llama, you can see, is also a very huge. You can see Llama 3.1 is the latest version. Not the latest version. Okay, the last year. It contains of more than 400 billion parameters. But they also released a lightweight pre-trained model, also contains only 70 billion parameters. Okay, so but all these models are very huge. So actually, although it's open source, but to tune the models, you still need a very strong computation resource to do it. Okay, so in our term project, we are going to do design a recommender system. The recommender system is you can choose your M model by yourself and collect your data, and we also we will introduce a technique called RAG, or use RAG. Okay, you can build your personal recommender system. Okay, so you can choose which LLM model you want to use, and just follow the RAG. Our assistant will show you the step and give you a baseline models, and then you can change the module by yourself or fine-tune the module. And next is Vision Transformers, is also published by Google. Okay, it's encoder. So it means the VIP Vision Transformer is trying to transform your image into a representation vector. And you can use this vector to do classification or to do segmentation or anything. Any computer vision related task, you can use this encoder to generate a good representation to do the following task. Okay, so this the original paper is from here. An image is worth 16 by 16 words was published in ICLR. It's the top, the best, top of top conference. Okay. So there's a general framework of the VIT. Okay, so you can check from here. Suppose I give you an image. The image is like this, and I want to transform this image into a vector of representation. Okay, so their idea is, okay, so I will divide the image into several blocks and several pages. Here we say pages. So here we can see there are 9 pages. Okay, so each page we can extract the features by using CNN or something else. Just use the raw data is also okay. Okay, so it's the first block, and the linear projection is just to flatten the pages because the image is 2D. Okay, I have to flatten it into just a vector. Okay. So now I get the linear projection. I get it's a first page representation, a vector here, the second page, the third page, here, and page. Okay, so in VIT they have some special design. At first, they have a position embedding. It's the same as the original transformers, but in here, because each page is associated with the location ID, right? You see, they have the location ID here, from 1 to 9. Okay, so each ID, position ID, give a spatial. It's learnable. So the position page is the position vector is learnable. You can think it's actually it's a linear layer. Okay, it can be learned. Okay, so that's what we call as a learnable position embedding. Okay, actually you can see from, you can see here, it's a learnable position embedding. So it's very simple, just like it's the first page is embedding, there's a second page, the embedding, and you just concat them together, and then finally plus with the position embedding. And the position embedding is learnable. You can think it's just a linear layer, and this layer's weight can be learned. Okay, so it's different from the original transformer. In transformers, they just use you see, they use this. It's a fixed equation. You cannot learn the position. You just use the fix, or just tune the parameters, but it cannot learn. But in VIT, you can learn it. Okay, so it's the first thing. It's different from transformer. And the second thing is they add a spatial extra. It's called a class embedded here. You see, it's the position ID is 0, and this mark shows it's a learnable class embedded. Okay, so you can think it's just another embedding, another vector here. Okay, so you can initialize as a random vector here, but after training it can be tuned. Okay, so all this in here we have from 0 to 9 we have 10 different embeddings, right? You can think there are 10 tokens. Okay, each tokens they have their own vectors here, and then we put all them, input them to the transformer encoder part. It performs the self-attention, right? So it means each token I can learn the similarity between other tokens and then combine, do the linear combination to generate my new representation. Okay? So the encoder here, finally, each token I will generate a new representation here. But I only keep this one. I will skip all the other tokens. I just drop it out. I don't use them. I only use this one's output. Okay, it's called the encoder output Z. 0. 0 means its location. Here. I just keep this one. All the others I just throw away. And I use this one to do as my final head to do the prediction, to predict what's the category of this image. Is try to do the classification test. Okay, so it's a general idea. Any problems? Okay, see here is the system diagram. You can see the flow is from your embedded page, and the node. Is a node means a layer node. Okay, also in transformer they apply the layer node. Okay, you know there are some different normalization like page normalization or layer normalization. So here they perform layer normalization. And so the multi-head attention. And here, this is a special design called residual, add residual here. Okay, the idea is from the ResNet. It's a very famous network widely used in computer vision. So it's just add the original vector back, concatenate with your attention, and then perform a node. It's again the layer normalization, and it's a multi-layer. As a multi-layer perceptron. Okay, it means it contain maybe two linear layers, and with some activation function like the loop or signal like this. And the P, you can design by yourself. Okay, then here we do the residual, add the residual back again, or repeat again. Okay. And then we will repeat this block at all times, and final output your final representation. Okay, and at the top is the mathematical expression for the whole process. So actually they just express the flow, express it in a mathematical form, like this. So Z0 means your token. Z0 is actually it's X class. X class is this one. And the next one is the first page is debating. Okay, here. And there is a second page here. Okay, you just concatenate together plus with your position embedded. It's called the Z0, means it's at the zeroth block. Okay. And the next we will, because we have in total L blocks, we have L blocks. The transform attention block L. So for each block from 1 to L, okay, each time you just perform, okay, it is a layer normalization here, layer normalization, and then they do multi-head self-attention here, and the plus with your residual here. Okay, and then to the next, I will do again, do the layer normalization, match to this. And the next is MLP, multi-layer perceptron here, and the plus your residual here. And you just repeat this process at all times. Just repeat, simulate the process at all times. And finally, after you finish, you just output your final output. I just take the 0 means I just use this token, the zero bills token, to do the layer normalization and to output to do your prediction. Okay, any problems? Okay, so let's just a brief review about the transformer family. Okay, we can take a break for 15 minutes. Okay. Next, I will talk about the widely used evaluation metrics in information retrieval.